Good day, sir. So for today's video, I'll be discussing about my answers in refrigerant chapters 11, 12, and 13. So first, we need to solve the first problem, of course, the 11-1. So an ammonia compressor has a 5% clearance volume and a displacement rate at 80 liter per second and pumps against a condensing temperature at 40 degrees Celsius for the two different evaporating temperature of -10 and 10 degrees Celsius. Compute the refrigerant flow rate assuming that the clearance volumetric efficiency applies. So we need to solve for us to get the answer. So at letter A, at -10 degrees Celsius from table A-3, S1 is equals to 5.7550 kilojoule per kilogram. Next is B sanction is equals to 417.477 liter per kilogram. At 40 degrees Celsius, constant entropy from figure A-1, V this is equals to 112.5 liter per kilogram and M is equals to 5%. So first we need to solve the clearance volumetric efficiency. So first the solution, 100 minus M multiplied to V summation over V this minus 1. To simplify that, 100 minus 5 multiplied to 417.477 over 112.5 minus 1, and the answer is 86.445. So next, we need to solve for the mass flow rate. So for the solution, VD times NC over 100 times resumption. To simplify that, 80 times 86.445 over 100 times 417.477, and we already solved the first mass flow rate, which is 166 kilogram per second at -10 degrees Celsius. Next, we need to solve the letter B at 10 degrees Celsius. From table A-3, S1 is equals to 5.924 kilojoule per kilogram K. V function is equals to 205.22 liter per kilogram. At 40 degrees Celsius, constant entropy from figure A-1, V this is equals to 90 liter per kilogram. M is equals to 5%. So the same process above. To simplify, 100 minus 5 multiplied to 205.22 over 95 minus 1, and we have our answer 94.199. To solve next, for mass flow rate, again the same process, and to simplify, 80 times 94.199 over 100 multiplied to 205.22, and we have our second mass flow rate, which is 0.367 kilogram per second at 10 degrees Celsius. So again, at 10 degrees Celsius, we have our answer 0.166 kilogram per second, and at 10 degrees Celsius, 0.367 kilogram per second. So for our next problem, 11-3, the catalog for refrigerant 22 4-cylinder metric compressor operating at 29, a condensing temperature of 40 degrees Celsius and an evaporating temperature of -4 degrees Celsius shows a refrigeration capacity of 115 kilowatts. At these operating points, the motor, whose efficiency is 90%, draws 34.5 kilowatts. The cylinder is 87 mm and the piston stroke is 70 mm. The performance data are based on 8 degrees Celsius of subcooling of the liquid leaving the condenser. Compute the actual volumetric efficiency and the compression efficiency. So for the second solution for our second problem, from table A-6 at -4 degrees Celsius, evaporating temperature H1 is equals to 403.876 kilojoule per kilogram. This suction is equals to 53.5682 liter per kilogram. S1 is equals to 1.75775 kilojoule per kilogram K. At table A-7, constant entropy, 40 condensing temperature, H2 is equals to 435.391 kilojoule per kilogram. V this is equals to 17.314 liter per kilogram. So first, displacement rate, it is equals to 4 cycle times 29 times 0.087 squared times pi over 4 times 0.07 is equals to 0.04827 meter cube per kilogram. To simplify, we have the answer 48.27 liter per kilogram. So to solve the actual rate of refrigeration flow, so 115 kilowatts over 403.876 minus 239.23 kilojoule per kilogram is equal to 0.6985 kilogram per second. So to solve for actual volumetric rate at the compressor suction, 0.6985 times 53.5682 is equals to 37.42 liter per second. So to compute the actual volumetric efficiency is equals to volume flow rate entering compressor over displacement rate compression. To simplify, 37.42 over 48.27 times 100 is equals to 77.5%, and that is the final answer for letter A. Next, for letter B, to solve for the actual work of compression is equals to 0.9 times 34.5 over 0.6985 is equals to 44.45 kilojoule per kilogram. So to solve the compression efficiency, in the solution for that is isentropic work of compression over actual work of compression multiplied to 100. To simplify, 435.391 minus 403 minus 876 kilojoule per kilogram over 44.45 kilojoule per kilogram multiplied to 100, and we got our final answer for letter B. For our compression efficiency, we have 70.9%. For our third problem, we have 11-4. An automobile air conditioner using refrigerant valve experiences a complete blockage of the airflow over the condenser, so that the condenser pressure rises until the volumetric efficiency drops to zero. Extrapolate the actual volumetric efficiency curve of figure 11-12 to zero and estimate the maximum discharge pressure assuming an evaporating temperature of 0 degrees Celsius. So, to discuss our solution, from figure 11-12, pressure ratio is equals to 5 plus 0 minus 67 over 56 minus 67 multiplied to 7 minus 5 is equals to 17.18. From table A-5, at 0 degrees Celsius, P suction is equals to 308.61 kilopascal. P, this is equals to 17.18 multiplied to 308.61. P, this is equals to 530.2 kilopascal. And that's our final answer. So next, for our next problem, or fourth problem, compute the maximum displacement rate of a two-compressor having a cylinder diameter of 190 mm and a rotor 80 mm long with a diameter of 170 mm. The compressor operates at 20 knots. So, solution. So, as you can see in figure 11-12 diagram, we have the given 190 mm, 510 mm, 10 mm, 94.472, 95 mm, and 85 mm. So cross Hayden area is equals to 1/2 times 3.3525 times 0.095 squared plus 1/2 times 0.094472 times 0.01 times 2 minus pi over 2 times 0.085 squared is equals to 0.004725 meters squared. So for D, it is equals to 2 multiplied to CA times L times relative speed. Simplify that. 2 is equals to 2 multiplied to 0.004724 times 0.08 times 29 is equals to 0.219 meter cube per second. So we have our final answer at 21.9 liter per second. If problem 11-6, a two-stage centrifugal compressor operating at 60 is to compress refrigerant 11 from an evaporating temperature of 44 degrees Celsius to a condensing temperature of 250 degrees Celsius. If both wheels are to be of the same diameter, what is this diameter? So, solution. At 4 degrees Celsius, evaporating temperature from table A-4, H1 is equals to 390.93 kilojoule per kilogram. S1 is equals to 1.68888 kilojoule per kilogram K. So, at 35 degrees, condensing temperature from figure A-2, S is equals to constant. H2 is equals to 410 kilojoule per kilogram. So, to solve, V sub 2T squared is equals to 1000 times H sub 2 minus H sub 1 over 2. To simplify, 1000 times 410 minus 390.93 over 2. And we have our answer, 97.65 meter per second per stage. From section 11-25, refrigerant 11, 113.1 meter per second tip speed. dW sub 1 is equals to 0.6 meter at 97.65 tip speed. dW, or the diameter, sub 2 is equals to 97.65 over 113.1 times 0.6 meter, and we have our final answer of 0.52 meter. So now from chapter 12, we have here the problem 12-1. An air-cooled condenser is to reject 70 kilowatts of heat from a condensing refrigerant to air. The condenser has an airside area of 210 meter squared, and the U valve based on this area of 0.037 kilowatts per meter squared K. It is supplied with 6.6 meter cube per second of air, which has a density of 1.15 kilogram per meter cube. If the condensing temperature is to be limited to 55 degrees Celsius, what is the maximum allowable temperature of inlet air? So our solution, first we have our given is 210 meter squared. VO is equals to 0.037 kilowatts per meter squared K. Q is equals to 70 kilowatts, and P is equals to 115.15 kilogram per meter. Our density is equals to 1.15 kilogram per meter. Condensing temperature is equals to 55 degrees Celsius. So the flow rate is equals to 6.6 meter cube per second over 1.15 kilogram per meter cube is equals to 5.739 kilogram per second. So Tp is equals to 1.0 kilojoule per kilogram K. LMTD is equals to Tc minus Ti minus Tc minus To over Ln multiplied to Tc minus Ti over Tc minus To. So UOAO LMTD. LMTD is equals to Q over AOVO equals to simplify 70 over 210 times 0.037 is equals to 9.009 K. Q is equals to WCP TO minus TI is equals to Q over WCP is equals to 70 over 5.739 times 11 equals to 12.197 K. LNTD is equals to TO minus TI over LN times 55 minus TI 55 over 55 minus TO. So the answer is 33.8724. So to simplify, 3.8724 times 55 minus 12.197 minus Ti, and the answer for we have the answer for Ti is equals to 38.6 degrees Celsius. For the next problem, 12-2, an air-cooled condenser has an expected V valve of 30 based on the airside area. The condenser is the transfer 60 kilowatts with an airflow rate of 15 kg per second entering at 35 degrees Celsius. If the condensing temperature is 48 degrees Celsius, what is the required airside area? So to solve for our solution, UOAULMTD, Q is equals to WCP times TO minus TI. W is equals to 15 kg per second, which is the airflow rate. CP is equals to 1.0 kJ per kilogram. K, TO is equals to TI plus Q over WCP. So, to simplify, 39 degrees Celsius is the TO. So, solution, LNTD is equals to TO minus TI over LN times TC minus TI over TC minus TO. To simplify, 39 minus 35 over LN times 48 minus 35 over 48 times 39 is equals to 10.878 K. So, 60 is equals to multiply 30 over 1000 AO times 10.878 K. So, to get the AO, we have our final answer, 184 meters squared. So, for our next problem, 12-10, a condenser manufacturer guarantees that V-valve operating conditions to be 990 based on the waterside area. In order to allow for fouling of the tubes, what is the V-valve required when the condenser leaves the factory? So, solution. So, 1 over VO2 is equals to 1 over VO1 minus AO over HFFAI. VO is equals to 900. So, and 1 over HFF is equals to 0.00176 meter per kilowatts. So, to solve, AO over AI is equals to 1.0. 1 over VO2 is equals to 1. To simplify, 1 over 900 minus 0.00176 multiplied to 1. And we have our final answer, VO2 is equals to 1.199. For the next chapter, 13, our next problem is 13-3. A refrigerant 22 refrigerating system operates with a condenser temperature of 35 degrees Celsius and an evaporating temperature of negative 10 degrees Celsius. If the vapor leaves evaporator saturated and is compressed isentropically, what is the COP of the cycle? If saturated liquid enters the expansion device and if the refrigerant entering the expansion device is 10% vapor, as in figure 13-3. So, solution. From table A-6 at negative 10 degrees Celsius, H1 is equals to 401,555 kJ per kilogram, S1 is equals to 1.76713 kJ per kilogram. At 35 degrees Celsius, constant entropy from table A-7, H2 is equals to 435.212 kJ per kilogram. So, to solve the problem A, at 35 degrees Celsius, saturated, H3 is equals to HF is equals to 240.114 kJ per kilogram. H4 is equals to H3, COP is equals to H sub 1 minus H sub 4 over H sub 2 minus H sub 1. To simplify, 401.555 minus 243.114 over 435.212 minus 401.555, and the answer for that is 4.71. So for the problem B, H3 is equals to HF plus X times Hg minus Hf. Hg is equals to 415.627 kJ per kilogram. H8 is 240.114 kJ per kilogram. and x is equals to 0.10. H3 is equals to 243 minus 114 plus 0.1 times 415.627 minus 243.114. H3 is equals to 260.365 kilojoule per kilogram, and it is equal to H4. So, to solve the COP, H1 minus H sub 4 over H sub 2 minus H sub 1. To simplify, again, 401.555 minus 260.365 over 45.212 minus 401.555. And the answer for that is 4.20. The next problem from chapter 13-4. Refrigerant 22 at a pressure of 1,500 kilopascal leaves the condenser and rises vertically 10 meters to the expansion valve. The pressure drop due to friction in the liquid line is 20 kilopascal. In order to have no vapor in the refrigerant entering the expansion valve, what is the maximum allowable temperature at that point? So, to solve the solution, we have our given P sub 2 is equals to P sub 1 minus G, or minus the gravity, H over V sub 1 minus P. H is equals to 10 meter and G, which is the gravity, given gravity 9.81 meter per second, and P is equals to 20 kilopascal, and P sub 1 is equals to 1,500 kilopascal. So from table A-6, V sub 1 is equals to 0.8808 liter per kilogram, and simplify 0.0008868 meter cube per kilogram. P sub 2 is equals to 1,500 times 1,000 minus 9.81 times 10 over 0.000888808 minus 20 times 1,000, and the answer is 1,368.62 kilopascal. So from table A-6, P sub 2 is equals to 35.4 degrees Celsius. So for the next problem from chapter 13-5, a superheat controlled expansion valve is in our refrigerant 22 system is that it's not equipped with an external equalizer. The valve supplies refrigerant to an evaporator coil and comes from the factory with a setting that requires 5K superheat in order to open the valve at an operator temperature of 0 degrees Celsius. So, the problem A, what is the difference in pressure on opposite sides of the diaphragm is required to open the valve? And the problem B, when the pressure at the entrance of the evaporator is 600 kilopascal, how much superheat is required to open the valve if the pressure drop at the refrigerant through the coil is 55 kilopascal? Solution. So, assuming from a parabolic curve, y sub 2 minus y sub 1, and it's equal to A multiplied to x sub 2 squared minus x sub 1 squared plus B x sub 2 minus x sub 1. At 5 degrees Celsius, evaporator temperature 5K superheat, 100 kilopascal pressure differential. X sub 1 is equals to 5 degrees Celsius and x sub 2 is equals to 5 degrees Celsius plus 5 degrees Celsius, and it is equals to 10 degrees Celsius. Yes, x sub 2 is equals to 10 degrees Celsius. So, y sub 2 minus y sub 1 is equals to 100 kilopascal. So, to solve the y sub 2 minus y sub 1, A is equals to 10 squared minus 5 squared plus B multiplied to 10 minus 5. So, 100 kilopascal is equals to 75A plus 5B. That is the equation 1. At 30 degrees Celsius, evaporator temperature. At 12 degrees Celsius, superheat. 100 kilopascal pressure differential. X sub 1 is equals to negative 30 degrees Celsius. X sub 2 is equals to negative 30 plus 12 is equals to negative 18 degrees Celsius. So again, the y sub 2 minus y sub 1 is equals to 100 kilopascal. Again, same process. 100 equals to A multiplied to negative 8 squared minus negative 30 squared plus B negative 8 minus negative 30. So 100 is equals to negative 576A plus 12B. And that is the equation number 2. To solve the equation 1 and 2, to combine that. So, for the first, the equation 1, we have here the 75A plus 5B. So, 41.667 equals to 240A plus 5B. And negative 100 is equal to 75A plus 5B. And it's equal. And A, we have our A at 0.185185. So B, we have 75 times 2, 0.185185 plus 5B. So we got our B, 17.2222. Therefore, y sub 2 minus y sub 1 is equals to 0.185185 multiplied to x sub 2 squared minus x sub 1 squared times or plus 17.2222 times x sub 2 minus x sub 1. So A at 0 degrees Celsius, evaporator temperature 5K superheat. X sub 1 is equal to 0 degrees Celsius, and x sub 2 is equals to 0 degrees Celsius plus 5 degrees Celsius is equals to 5 degrees Celsius. So y sub 2 minus y sub 1 is equals to 0.185185 multiplied to 5 squared minus 0 squared is plus 17.222 multiplied to 5 minus 0. And we have our answer 90.74 kilopascal. So next, letter B at 0 degrees Celsius, evaporator temperature. P is equal to 497.59 kilopascal. A sub P is equal to 600 kilopascal plus 55 kilopascal minus 497.59 kilopascal is equal to 157.41 kilopascal. X sub 1 at 0 degrees Celsius, 157.41 is equal to 0.185185 multiplied to x sub 2 squared minus 0 squared plus 17.222 multiplied to x2 minus 0, and the x sub 2 is equals to 8.4 degrees Celsius, which is equals to x sub 1, and the answer is 8.4 K. For our last problem, 13-6, the catalog of an expansion valve manufacturer specific a refrigerating capacity of 45 kilowatts for a certain valve when the pressure difference across the valve is 500 kilopascal. The catalog ratings apply when vapor-free liquid at 37.8 degrees Celsius enters the expansion valve when the pressure difference across it is 1,200 kilopascal. So solution, velocity is equals to C square root of 2 multiplied to pressure difference meter per second. Refrigerating capacity, then new refrigerating capacity is equals to 45 kilowatts square root of 1,200 kilopascal over 500 kilopascal is equals to 69.7 kilowatts.